For this video, I'm going to show two examples of how to solve problems that include the capability, Cp-Cpk ratios, and also do the defect rates. Some of you may not care about learning how to do the defect rates, and so I will do both Cp-Cpk first and interpret them, and then I'll do the defect rates for those that might be interested. So the first question says this: a part has a feature that is supposed to have dimensions of 3.5 plus or minus 0.05 centimeters. You have a sample of 30 parts. For the sample, the mean is 3.495 centimeters and the standard deviation is 0.0139 centimeters. Is the process capable? What is the defect rate? Now, whenever a problem asks, is the process capable, what I would like you to do is find both the Cp and the Cpk. So that's what we're going to find first, is the Cp and the Cpk ratios. So the Cp ratio is equal to the upper specification limit minus the lower specification limit divided by 6 times the standard deviation of the process. In this problem, the upper specification limit is 3.5 plus 0.05, so it's 3.55 centimeters minus 3.45 centimeters. That's 3.5 minus 0.05. And then that's going to be divided by 6 times the standard deviation, 0.0139. I'll put my calculator to solve those in a moment. The Cpk is equal to the minimum of the upper specification limit minus x bar divided by 3 times the standard deviation of the process. I don't know why the camera keeps shutting off on me. And x bar minus the lower specification limit divided by 3 times the standard deviation of the process. In this case, that gives us minimum of 3.55 minus the x bar is 3.495 divided by 3 times 0.0139 and 3.495 for my x bar minus 3.45 for my lower specification limit divided by 3 times 0.0139. My notation's inconsistent there. 0.02. All right. And I will solve those. All right. So I'll put my calculator in here to solve them. This time, anyway. I have 3.55 minus 3.45. That gives me 0.01. I'm going to divide that by 6, and then I'm going to divide it again by 0.0139. And that gives me a CP of 1.199. I could probably have rounded that to 1.12. For the CPK, I'll do this a side at a time. So for the first part, we have 3.55 minus 3.495 divided by 3 divided by 0.0139. So that gives me 1.32. We'll round it. Now, you'll notice that's larger than the CP. That means the other side is the one that we're actually going to use. It'll be the minimum. what you get with these, remember the CP is the theoretical maximum capability, assuming the process is perfectly centered. The CPK tells me the capability based on how the process is now currently operating. So the highest the CPK can ever be is the CP. The CP is a bound on the CPK. So let's go ahead and do the one that we know will be the right number now. 3.495 minus 3.45 divided by 3 divided by 0.0139 is 1.79. Now the minimum of those two is the smaller, 1.0, and I'll go ahead and round it, 1.08. So the answer is the CP is 1.12 and the CPK is 1.08. Therefore, we could say this process is capable because both the CP and the CPK are greater than 1. Now, I probably should have done this first. I'm going to go ahead and draw a picture of this particular problem. So I'm going to use this little picture to find the defect rate in a minute. But I'm also going to use it to explain the difference between the CP and the CPK. So the mean is a little smaller than the target, if you will, the middle of the specification band or range. So it probably looks something about like this. This is 3.495. This is 3.45. This is 3.55. All right. What's out here in the tails is the defects or the defects. So it's a defect if it's smaller than the lower specification limit or larger than the upper specification limit. And so I can just find z-scores in order to find those defect rates. But let me flip this over and show why the CP and CPK are used. So I'm going to draw a specification band. We'll use the one we're on for this problem. This is 3.45. This is 3.55. And I'm going to draw basically what we have. We have a distribution that looks kind of like this. And we just found that the CP was 1.12 and the CPK was equal to 1.07. I'm going to now replicate that here. I'm going to try to draw this. This is, again, 3.45, the lower specification limit, 3.55, the upper specification limit. Now let me draw this. Suppose that instead of this situation, we had this situation where it's off-centered. Now, I know that's not quite the same. I tried to draw it so the curve is exactly the same as this curve. Now, I know it's not, but I think everyone would agree that this is a much worse situation for a company to be in if this is a machine they're using. Because here, the defect rate's very low. We'll solve for the defect rate on the other side in a minute. But for now, you can all agree that this is a much higher probability of a defect than whatever's going over here. But if you look at the CP formula, the CP formula is going to give you exactly the same number. Because again, the CP is equal to the upper specification limit minus the lower specification limit divided by 6 times the standard deviation of the process. Because it doesn't care where my mean is, it's going to give you the same answer. So this should probably have a CP of about 1.12 as well. But the CPK would be much less, because what the CPK does is it looks at the distance between your X bar and the upper specification limit and X bar and the lower specification limit, and divides those numbers by half of the width of the distribution. So the CP ratio looks at this width, the specification band, and then it says, well, the natural width of the distribution, I drew those too small, is about 3 standard deviations. So if I put 6 standard deviations on the bottom, this is the spread of the variance, and this is what they call the specification or tolerance band? How wide is it? So here, instead, what we're doing with the CPK formula, we take the minimum of these two numbers. The first number, upper spec limit minus x bar divided by 3 sigma, takes a look at the distance between x bar and the upper spec limit, and then it divides it by 3 sigma, or half kind of the width of the distribution. And then the other half of the CPK formula looks at the distance between x bar and the lower specification limit here, and then also divides it by 3 sigma. 1, 2, 3. That's why you should always find both of them. And the CP gives me the specification or the capability, assuming the process is perfectly centered. The CPK gives me the capability as it's currently operating. If you were to only use one, you should use the CPK because it takes into account whether or not that organization or that machine is able to keep the process centered. But for the purposes of the class that I'm teaching, and I would hope going forward if you ever do capability analysis, you would find them both. They're easy. The CP gives you the theoretical capability if it were perfectly centered. The CP tells you how it is, how it's operating now. I have a second example to do. Another part has a feature that is supposed to have dimensions of 5 plus or minus 0.03 centimeters. You have a sample of 30 parts. The sample mean is 5.011 centimeters, and the standard deviation is 0.0088 centimeters. Is the process capable? And again, what is the defect rate? So let's go ahead and solve this. I already wrote the equations out. So the CP is equal to the upper specification limit, which in this case is 5.03 minus the lower specification limit, which is going to be 4.97, divided by 6 times 0.0088. Find that in a minute. CPK is going to be equal to the minimum of 5.03 minus 5.011 divided by 3 times 0.0088 and 5.011 minus the lower specification is 4.97 centimeters divided by 3 times 0.0088. All right, so now we can plug that into our calculator. Let's have it on my phone. 5.03 minus 4.97 divided by 6 divided by 0.0088 gives me a CP of 1.114. Round it up. For the CPK, I'm going to have the minimum of 5.03 minus 5.011 divided by 3 divided by 0.008. 0.72. So we can already see it's not going to be capable. I'll do the other side for completeness sake. Mean minus the lower spec limit divided by, got out of order there, 5.011 minus 4.97 divided by 3 divided by 0.0088. 1.55, but the minimum is the smaller, which is 0.72. So the CP is 1.14, the CPK is 0.72. Therefore, this process is not capable. But it would be capable if it were perfectly centered. Draw a picture of this process so you can see what's going on here. So the mean we said was 5.011, but with a 0.72, it's probably something like this and like this. So this is the 4.97, and this is the 5.03. And we have a few more defects here than we would like. On the other side, it's very small. All right, that's CP and CPK, how you interpret them. I'm now going to go ahead and do the defect rates as well. If you don't want to know how to do the defect rates, you can stop watching the video. All right, so we'll do the top one first. In this case, I said the first thing we do is find z-scores. You're going to find two z-scores. Remember, a z tells you how many standard deviations away one number is from the mean. And you can use a standard normal table then to find the probabilities of that. In this case, to find this probability, the z-score is going to be equal to 3.55 minus 3.495 divided by sigma, which was 0.0139. That gives me a z-score of 3.55 minus 3.495 divided by 0.0139, which equals 3.95, like 3.96, I guess. It's not going to matter much for the table we're using. On the other side, so this area here is equal to the probability that z is greater than 3.95, 3.96. On the other side, z is going to be equal to 3.45 minus 3.495 divided by 0.0139. Plug that into my calculator. 3.45 minus 3.495 is negative 0.045 divided by 0.0139. That gives me a z-score of negative 3.2, we'll round up to 4. So this probability can be written as the probability that z is less than negative 3.24. Now to find those two probabilities, I'm going to use a standard normal table. They're in every textbook. This is one that I use in some of my classes. It's a table that gives me the probability of being smaller than the z-score. So the first thing I'm going to do is look up 3.96. Now, if you look down here, the bottom of the table, it doesn't go that far. It only goes to 3.88. This is 3.80. This is 3.81, 3.82, 3.84, so on. So it only goes to 3.89, but it's saying the probability being in the tail is something less than, well, it gives me the probability of being less than the number. So if I want the probability of being up in this tail, I take 1 minus this probability here. So if we wanted the probability of being less than 2.92, it would be 0.9982. If we want the probability of being more than 2.92, we exploit the fact that the total area under the curve is 1 and the table is symmetric to take 1 minus 0.9982. So this little unshaded probability would be 0.0018 or 1 minus 0.992. So in our case, we're going to go with, estimate it with 1 minus 0.9999. So this probability here is actually less than, probably much less than 0.0001. And there are ways you could figure that out. You could find this number actually in Excel if we wanted to, but I'm just going to approximate it today. This one, the probability of being less than negative 3.24, well, if I use this table and look up 3.20, 3.20, 3.21, 3.22, 3.33, 3.24, the probability of being less than 3.24 is 0.9994. So the probability of being more than 3.24 would be 1 minus 0.9994, which would be 0.0006. Now that would be on the top side. But because it's symmetric, the probability of being greater than 3.24 is the same as being less than negative 3.24. So I know that this probability here is 0.0006, roughly. If I add the two probabilities together, I can conclude that the defect rate is less than, in this case, 0.0007. That would be a good approximation of the defect rate. Something a little smaller than that, probably. Let's do it for this problem as well. So for this one, I'm going to do exactly the same things. This probability, I'm going to find the z-score. Z is found by taking 5.03 and subtracting 5.011, dividing by the standard deviation, which was 0.0088. That gives me a z-score of 5.03 minus 5.011, 0.019 divided by 0.0088, 2.16, rounded that up slightly. On the other side, I'm going to have z equals 4.97 minus 5.011 divided by 0.0088. So that z-score, 4.97 minus 3.011 divided by 0.0088, negative 4.565. And we already know from looking at our table that this number is going to be something less, probably much less, but this is less than 0.0001. So it's less than that number. This one over here, though, we can find the probability that z is greater than 2.16. We'll that turned off again. We'll look at our table. 2.16 is right here. 0.9846. I know that might be hard to see. So I can focus that. Pen might be messing it up. Find that again, 2.16, 0.9846. If I take 1 minus 0.9846, I get 0.0154. So this probability equals 0.0154. If I go ahead and add that other thousandth in, or a little less, or sorry, 10,000th in, I get the defect rate is actually less than 0.0155. There's an approximation of the defect rate as well in this problem. Hopefully that's helpful if you want to find the defect rates, and also to find the CP and the CPK, or the capability of the machine in producing to the specification limits. I'm going to tack on a little warning. We've also been finding control limits. Remember, specification limits and control limits are different. Specification limits are set by the engineer, the designer, perhaps the customer or a manager, where the control limits are a statistical artifact of the variability of the process. So just be sure not to get those confused. And I hope this video proves somewhat helpful to you.